All right, well, similarly to the energy stored in a capacitor, we now have an equation that we can use to determine how much energy is stored in an inductor after we energize that coil. So let's say we have an example where we pulse a source from initially 0 up to, let's just say 50 volts. And let's say that I've got an inductor here, and I've got a resistor here of 50 kilo ohms, and let's say that my inductor is a 0.1 millihenry inductor, okay? And what I want to know is, so initially let's say IL of t equals 0 is 0, and this is obviously IL of t. And I want to know what is the energy stored in the inductor evaluated at t equals, let's say, around 10 tau, again, like we did last time. So we know that the inductor will fully energize after around 5 time constants, similarly to the capacitor charging at around 5 time constants. So 10 time constants later should be at the full final value of the current. Well, if we recall correctly, once the inductor is just behaving like a short at DC, this voltage will be 50 volts because this will have pulsed. Let's also just make it clear that this makes its transition at t equals 0 to 50. And so the final value here is that we're going to have a short here. This voltage here will be 50 volts, and I'll have 50 volts across a 50 kilo ohm resistor, which means my current, my final current, will be 1 milliamp, okay? And so all I need to do now to determine the energy stored in my inductor as a function of the current is equal to 1/2. My inductance is 0.1 times 10 to the minus 3 henries, or 0.1 millihenries, multiplied by 50 times 10 to the 3, which is 50K. Oh, sorry, I'm not the resistance. It's the current that I'm interested in. 1 times 10 to the minus 3 squared. All right, and so I get 1/2 times 0.1. Or sorry, let me just throw this on my calculator. I don't feel like trying to do the mental math. So it's going to be 0.1 times 10 to the minus 3. And then I have 10 to the minus 3 squared. Gotta add these up. 0.1 times 10 to the minus 3. And then I have 10 to the minus 6 multiplied by this. And I divide by 2. I get 50 picojoules. That is a really, really tiny amount of energy. Okay, so EL of ILF gives me 50 times 10 to the minus 12 joules, or 50 picojoules of energy. Okay, that is a very small amount of energy. It's because the current is so small and the inductance is so large. If I had a larger current flowing through the inductor, I'd have more energy. Obviously, that's what this equation tells me. But obviously, just want to get an example out there where I show this equation being used in an example, okay? So now that we have covered this energy stored in an inductor, we can move on to de-energizing the coil. And once we finish that, we are pretty much done with this module. So I'm going to go ahead and wrap this video up right here, and we'll move on to the next video.